Hi everyone. In this video, we are going to discuss about the necessary conditions for the two roots of a quadratic equation to be greater than a certain real number. Let's assume that we have a quadratic equation like ax squared plus bx plus c is equal to 0. And because it is a quadratic equation, obviously it will have two roots. And here we are going to investigate what would be the necessary conditions if the two roots of this equation has to be greater than a certain real number. So let's assume that the quadratic expression which is on the left hand side of the equation as f of x, and I have it written here in the pink color. So f of x is equal to ax squared plus bx plus c, and we're going to look at the possible graphs of this function to determine the necessary conditions for the two roots to be greater than a real number k. So here I have noted that alpha and beta, they both have to be greater than k, and we're going to find out what are the necessary conditions for that, right? First, we are going to discuss about the quadratic function graph when the leading coefficient is positive. So I have two graphs here when the leading coefficient is positive, and when the leading coefficient is positive, we know that the parabola opens upwards. Now, if you are thinking that why I don't have the other graph where the parabola does not even touch or cut the x-axis, well, because we are talking about two real roots, the discriminant either has to be 0 or greater than 0. It cannot be negative. If the discriminant is negative, then we don't have two real roots, and in that case, the study of roots being greater than a real number would not even make sense. So because we are going to do the study of both roots of a quadratic equation being greater than a real number, we have to make sure that the quadratic equation has real roots. So that gives us the first necessary condition, that the quadratic equation has to have real roots. Whether the roots are distinct or they are equal does not matter, but they have to have real roots. That means the discriminant cannot be negative. That is our first necessary condition. So I'm going to make a note right here. So here I have noted that d must be greater than or equal to 0, and that is our condition number 1. Now let's talk about the second condition. If you look at the two diagrams here, I have the two parabola graphs here. In the first one, I assume that the discriminant is greater than 0, and in the second graph I assume that discriminant is equal to 0. That means we have two equal roots there, and in the first diagram we are assuming that the function has two distinct roots. And here on the positive x-axis I have noted the point which is at k comma 0. That means that's the point which represents the real number k, and the roots have to be greater than k. That means the roots have to be on the right hand side of that point, and that is how I have both the diagrams there. You can see that the parabola is actually on the right hand side of that point, meaning it's cutting the x-axis or touching the x-axis on the right hand side of that point, right? Now, what other condition can help us guarantee that the parabola will be touching or cutting the x-axis on the right hand side of that point? Well, one of the things that we can check is obviously the vertex of the parabola. So let me highlight the vertex right here. I'm highlighting with a red dot there, and here also we have the vertex. On the second diagram also we have a vertex here. Now, if we can somehow make sure that the vertex is also on the right hand side of the point k, then to some extent we can guarantee that yes, the roots will be greater than k. Well, there is a chance that the roots should be greater than k, but it's not always guaranteed. Why? I will show you very soon. So first, let's do this condition that if the roots have to be greater than k, then the vertex also must be greater than k, meaning the x coordinate of the vertex must be greater than k. So if that is the vertex, then what is the x coordinate? Well, the x coordinate would be somewhere right here. I have a red dot on the positive x-axis right here, and on the second diagram it's the same point where we have the vertex, and that is the x coordinate of the vertex on the second diagram. In the first diagram, the x coordinate of the vertex is denoted with a red dot right here on the positive x-axis. Now, what is the x coordinate of the vertex? Well, the x coordinate of the vertex is negative b over 2a. So here I am going to note down the second condition. In the second condition, we are going to say that the x coordinate of the vertex must also be greater than k. Think about it, because we have to make sure that the roots are greater than k, right? So at least we can say, hey, if your vertex is greater than k, then there is a fair chance that the roots also could be greater than k, right? If the vertex is on the left hand side of k, then obviously the roots will be less than k, right? If the vertex is not greater than k, then we really cannot guarantee that the roots will be greater than k, right? So the second necessary condition is that the x coordinate of the vertex must be greater than k. Here I have noted negative b over 2a greater than k. That's our second necessary condition. Now the question is that going to guarantee that both the roots will be greater than k? Well, not really. Why? Let's take a look. Now look at this one region right here that I'm highlighting in the green zone right here. On the positive x-axis in the first diagram, within the parabola, I mean between the two roots right there, if you look at this green portion right here in the first diagram, that vertex greater than k could also mean that the k could be in that green zone also. If k is located anywhere in that green portion right there on the x-axis, then also your vertex will be greater than k, but guess what? One of the roots will be less than k. The smaller root will be less than k, because here is one root right here. I'm doing a red dot again right here to indicate that hey, this is the smaller root and this is the larger root right there. I have highlighted both of them. Now if you look at that green portion right there, if k is located in the green portion, then also the x coordinate of the vertex will be greater than k. However, the smaller root will be less than k. So we really could not guarantee that both roots will be greater than k. Now to guarantee that both roots will be greater than k, somehow we have to make sure that k is not inside the parabola. I mean k is not between the two intersecting points of the parabola. So somehow we have to bring k outside of the parabola. So far the two conditions that we have, they do not guarantee that k will not be inside the parabola. Somehow we have to find a condition where we can guarantee that k will be outside of the parabola. Now what could be that condition? Well, so let's try this condition. Now I am going to show you one little trick right here. So suppose at k, what would be the value of the function? If I somehow connect it to the function right here, so this will be the value of the function. This will be f of k. This point, the yellow dot right here on the function graph, that would be f of k. Think about it. Now in this case, f of k is obviously greater than 0. You see f of k is positive because k is outside of the parabola. When k is outside of the parabola, f of k is positive. If k is inside the parabola, then guess what? F of k will be negative. You look at it right here. In case k is inside the parabola, say suppose a point right here like a yellow dot, and you see the f of k right here, this f of k, if k had been there, right? K is not actually there, but if k had been there, then f of k, this point right here on the first diagram, the point on the lower part of the parabola there, that f of k will be a negative number. It will be a negative value. So when the leading coefficient is positive, we see that f of k will be positive if k is outside of the parabola, and f of k will be negative if k is inside the parabola. Now using the same concept, I am going to show you the two other diagrams where we will see when the leading coefficient is negative, what would be the value of f of k. So let's take a quick look. And here, when the leading coefficient is negative, I have two diagrams here, and if k is somewhere here, you see, let me plot k right there. Say suppose this is our k right here on the positive x-axis. Let's suppose this is k comma 0, that point is k comma 0. And then what would be the value of f of k? If you carefully look at it, you will notice that f of k is actually negative. So f of k will be somewhere over here, that would be f of k, and that is a negative value. But if k is somewhere inside the parabola, for example, if k is right here, then guess what? F of k will be a positive value right there, because this will be the f of k then right here, and then f of k would actually be positive when k is inside the parabola. When k is outside the parabola, f of k is negative. When k is inside the parabola, f of k is positive. Now look at both the diagrams or both the situations there, right? When leading coefficient is positive versus leading coefficient is negative, right? When leading coefficient is positive, if we multiply a with f of k, that product will be positive. When leading coefficient is negative, then also if we multiply a with f of k, that product is also going to be positive, assuming that k is outside of the parabola. When k is outside of the parabola, f of k is negative and a is also negative, and their product will be positive. So whether a is positive or negative does not matter if we consider a condition like a times f of k greater than 0, that will guarantee that k is not inside the parabola, k is outside the parabola. I hope it is making sense. So from here, we are going to note down our third condition that, hey, if we take a product of a times f of k, and if we can guarantee that that is greater than 0, then we can guarantee that k is outside of the parabola, not inside. And that's exactly what we want. Then we are 100% sure that, hey, both roots will be greater than k, because we are already keeping k on the left hand side of the vertex. And now through the third condition, we are going to make sure that k is not inside the parabola, k is outside of the parabola. That way, using these three conditions, we can safely guarantee that both roots of the quadratic equation will be greater than k. So let's make a note of the third condition. So I have noted the third condition here, that a times f of k must be greater than 0 to guarantee that both roots will be on the right hand side of k. That means both roots will be greater than k. So those are the three necessary conditions to guarantee that both roots of a quadratic equation will be greater than the real number k. Now that we have determined the three necessary conditions for the quadratic equation to have both roots greater than k, I'm going to take a quick example and see how this concept can be used in an example, right? So let's take an example here. I'll make a quick note of the necessary conditions again. The first condition was that d must be greater than or equal to 0. And the second condition was that negative b over 2a must be greater than k. That's the x coordinate of the vertex. So the x coordinate of the vertex must be greater than k. And the third condition is that a times f of k must be positive. Now let's take this example. Let's suppose we have a quadratic equation like this, and here we have to find out for what values of p both roots of this quadratic equation, let's say alpha and beta, they both will be greater than, let's say, 3. So 3 is a real number. So here we have to find out for what values of p this quadratic equation will have both roots greater than positive 3. Right? So let's use these conditions one after another. The first condition is that the discriminant must be greater than or equal to 0. So what is the discriminant in this case? In this example, what is the discriminant? Well, so discriminant is b square minus 4 times a times c. So that's b square minus 4ac. Now what is b in this equation? Well, in this equation, let's make a quick note here. So for this quadratic equation, a is actually, the leading coefficient is actually 1 and b is actually p minus 5. And what is c? C is actually negative 5 times p. Negative 5 times p. Now what is the discriminant? Well, discriminant is actually b squared minus 4ac. So discriminant is b squared minus 4ac. Now if we substitute the values, then what is b squared? Well, b is actually p minus 5. So we can say p minus 5 whole squared, that is b squared minus 4 times a is 1 times c is actually negative 5p. And what is the first condition there? Well, the first condition says that the discriminant must be greater than or equal to 0. So then from here can we say, well, according to the first condition, this value must be greater than or equal to 0. So this value will be greater than or equal to 0 or has to be greater than or equal to 0. Now from here what can I say? Let's remove the parenthesis and let's do the whole square there. So p minus 5 whole square, that would be p squared minus 2 times p times 5, that would be negative 10 times p plus 25, that would be 5 squared. So a squared minus 2ab plus b squared, and then negative 4 times 1 times negative 5 times p, that would be negative and negative, positive 20 times p, and this must be greater than or equal to 0. And from here we can say, well, this is looking like p squared, then negative 10 times p and positive 20 times p, so this will give us positive 10 times p plus 25. So this must be greater than or equal to 0. And from here what can we say? Well, if you look at that expression carefully, it is actually p plus 5 whole square. It's like a squared plus 2ab plus b squared. So that is p plus 5 whole square. So we can write it as p plus 5 whole square, and that must be greater than or equal to 0. And if we use the wavy curve method, we can easily find that p will be any real number. To satisfy this condition, p can be any real number. Let me quickly draw a line here. So for this inequality, the critical point is negative 5, because if you equate p plus 5 to 0, then p would be equal to negative 5, and that would be the critical point. So if I plot the critical point somewhere right here, let's assume that this is negative 5, and on the right hand side of that point, any value on the right hand side will give us a positive zone there. So this is the wavy curve method, and here it is all positive. And on the left hand side, as you go to the left hand side, will it be negative or positive? Well, that depends on the multiplicity of this factor right here, the factor that gave us the critical point negative 5, and this is the same factor, its multiplicity is 2, meaning it has an even multiplicity. That means when you go to the left hand side of that point also, the value out of that expression will be positive. So both on the right hand side and left hand side it will be positive, because in this case the multiplicity of this factor is even, which is 2, right? It's a square, p plus 5 whole square. So that's an even multiplicity, so it will also give us a positive value. If we take any number which are on the left hand side of negative 5, then also this expression will give us a positive value. So that means we can take any value of p and we will get a positive result out of this p plus 5 whole square. So here we can say p can be any real real number. So we can write it like this. We can say p can take any value from negative infinity to positive infinity. That's as per the interval notation. Alright, so far we have looked at the first condition. Now let's look at the second condition and see what values of p we get. And one thing we have to remember that these conditions are actually AND conditions. That means whatever solution that we find from each of these conditions, we have to take an intersection of all the solutions. That means we have to take the common zone on the real number line for the value of p, where all three conditions would satisfy. And these are actually AND conditions, because all three conditions must be true to guarantee that both roots will be greater than the given real number. So let's quickly solve the second condition. The second condition is negative b over 2a has to be greater than k. So in this case, what is negative b over 2a? Negative b over 2a, that has to be greater than k. Now let's substitute the values. Well, what is k in this case? Well, in this example, k is actually 3. So this 3 right here, that is our k right here. That 3 is actually the k, because both roots have to be greater than 3. So if we substitute the values, then what we get? We can say, okay, what is b? b is p minus 5. So that is negative of p minus 5 over 2 times a is 1 actually. So that is greater than k, and k is 3. So that is greater than 3. So that is our condition there. Now from here, let's simplify a little bit and let's see what we get. We get negative p and positive 5. So that would be 5 minus p whole divided by 2. It will be greater than 3. And if we bring everything to the left hand side, what do we get? Well, from here we can say, well, then 5 minus p divided by 2 and minus 3, that has to be greater than 0. And if we simplify a little further, what do we get? Well, we get 5 minus p and then minus 6 whole divided by 2, that is greater than 0. And from here, what do we get? We get negative p and negative 1 whole divided by 2 greater than 0. And if we multiply both sides by 2, what do we get? We get negative p and negative 1 greater than 0. Now if we multiply both sides by a negative 1, what do we get? We get positive p and positive 1 less than 0. The inequality sign will flip, because now we are multiplying both sides by a negative 1. Now from here we can say, well, then p must be less than negative 1. And using interval notation, how can we denote it? Well, if p must be less than negative 1, then we can write it like this. P would belong to the set which should be from negative infinity up to negative 1, both excluded. Of course, infinity can never be included, and here negative 1 also must be excluded because it is strictly less than negative 1. So we have to exclude that. So far we have obtained two ranges of values, right? Let me quickly highlight them. From the first condition, we have obtained this one range right there, and then from the second condition, we have obtained this other range of values for p. And now we are going to take a look at the third condition quickly. The third condition is like this: a times f of k must be positive. That was the third condition. Now here, what is a? Let's substitute the values. Well, we know a is 1, so 1 times f of 3. In this case, k is actually 3, so this must be greater than 0. Now let's use 3 in place of x right here. So then in our quadratic expression, what do we have? So our quadratic expression was x squared. Let me quickly write it down here. So our f of x is that f of x is actually, in this particular example, it was actually x squared plus p minus 5 times x minus 5 times p. Now if we try to substitute the value of x in this quadratic function, what do we get? Well, from here, f of 3 would be, in place of x, we are going to use 3, right? So it would be 3 squared plus p minus 5 times 3. Wherever we have x, I am using 3, and then minus 5 times p. And that must be greater than 0. And now if we simplify it a little bit, what we are going to get? We are going to get 9 plus 3 times p minus 15 minus 5 times p. And all of that will be greater than 0. And then from here, we're going to simplify a little more, and we're going to say, okay, we have positive 9 and negative 15, that would be negative 6. And then we have positive 3p and negative 5p, so that would be negative 2p. All of that will be greater than 0. If we divide both sides by negative 2, what will happen? It will become 3 plus p. We are dividing by negative 2 on both sides, right? So negative 6 will become positive 3, and negative 2p will become just p because we are dividing by negative 2. And the inequality sign will flip because we are dividing by a negative number, and 0 divided by negative 2, that will be 0. So now the inequality is kind of looking like this. And from here, what can we say? Well, from here we get p less than negative 3. If you move 3 to the right hand side, then we get p less than negative 3. So we can say, well, from here we get p belonging to the set or the interval kind of like this. So it will be from negative infinity up to negative 3. Negative 3 excluded, of course, because it's strictly less than negative 3. So this is the third set of solution that we got for the value of p, right? So let me quickly highlight that. Now you have to take the intersection of these three sets. Now what are those sets? Well, if we carefully take a look at the three sets right here, so we have one set where we say p can be any real number, and in the second solution set we say that p must be less than negative 1, and in the third solution we say, well, p must be less than negative 3. So now let's plot all these solution sets on the real number line and see how that looks. So I'm going to draw a real number line here. So in the first solution set, we have p can be any real number, right? So let me use another color on top of the real number line to indicate that, hey, p can be any number on this line, right? So now I'm going to use a different color. So with that color, I'm denoting that, hey, p can be any number on the real number line. That is the first solution set. Now what is the second solution set? Well, the second solution set says that p has to be less than negative 1. Now what is less than negative 1? I'm going to use a small little circle here, hollow circle on top of negative 1. P has to be in this zone. Now I am showing it by the yellow color. So my yellow color is overriding the light green color there, right? So now this is the intersection of the first two solution sets. Now what is the third solution set? Well, the third solution set says that p must be less than negative 3. Well, now I'm going to use a red color maybe. So using the red color, I'm now going to do a hollow circle on top of negative 3 because negative 3 is excluded. So this is the zone right here where p has to lie, meaning p can take any value in the red zone. So p must be a number from the red zone. It cannot be a number from the light green zone. It cannot be a number from the yellow zone. It must be a number from the red zone because this is the zone where we have three of the sets overlapping. That means we are taking the intersection of the three sets, right? So this is the intersecting zone on the real number line, and that will be the ultimate answer. So we have to finally say, well, then the final answer is going to be like this. We can say, well, then therefore we can say p must be less than negative 3, or you can also write it like this: p belongs to the interval negative infinity through negative 3, and that is the answer for this question. So now that we know p has to be in this range, right? P has to be less than negative 3. Should we test a value of p just to see if it is making sense? Well, yeah, let's try with a value, maybe like a negative 4 maybe. Okay, let's try with negative 4 and see what happens. So now we are going to use a value of p which is equal to negative 4 to see how the quadratic equation behaves, or to see how the roots of this quadratic equation going to look like. So now I am going to use a value of negative 4 for p to see what would be the roots of this quadratic equation, and my assumption is that the roots will be greater than positive 3. So let's try that. So what is our quadratic equation? So that was our quadratic equation, and we are going to use a value of p which is equal to negative 4. So now I am trying this out with p equals negative 4, right? So let me make a quick note here. So I am going to use negative 4 for p and then see what are the roots of this equation, and we are hoping that the both roots will be greater than positive 3. So let's try it and see what happens. So from here, if we use negative 4 for p, then our equation going to look like this. It will be x squared plus, for p I am using negative 4, and then negative 5 was already there. Outside we have an x there, and then minus 5 times negative 4 because we are using negative 4 for p, and that is equal to 0. That's our quadratic equation. And from here, what do we get? Well, from here we can say this is actually x squared minus 9 times x. So that would be x squared minus 9 times x and plus 20. And from here, if you factor the expression, then we can write it as x squared minus 5 times x minus 4 times x plus 20 is equal to 0. This is just for factoring. And from here, can we say, so from here we can say, well, then if we take x as a common factor, so we have x minus 5, and then again negative 4 as a common factor, again we get x minus 5, and all of that is equal to 0. And then from here we can clearly see that we have two factors here. We have x minus 5 as a factor and x minus 4 as a factor. So from here we can say then x minus 5 will be equal to 0, or x minus 4 will be equal to 0. That means from here we can say, well, then x is going to be 5 or x is going to be 4. So what are the two roots that we found here? Well, here are the two roots. One is positive 5 and the other one is positive 4. So now if you think about it, both roots are actually looking like greater than positive 3. So here we can clearly see that both roots, if I denote this with alpha equals 5, let's say alpha is one of the roots and then maybe beta is equal to 4, that is the other root, then we can clearly say that both alpha and beta, they both are greater than 3, which was actually the value of k in our example, right? So we are seeing that yes, if we use any real number which are less than negative 3 for p, then this quadratic equation will have two real roots both being greater than positive 3. I hope everything made sense. Thank you for watching. See you in the next video.